Peter, time is yours, please. Go do your presentation.
Hello everybody. First of all, I would like to apologize because in the first email the information was that I have 90 minutes for my presentation. So I prepared 68 slides and now I have about 20 minutes, so I will skip.
Don't worry, that's like 45 minutes.
Okay, so maybe I will skip some basic slides. Okay, so let's start about our department. As colleague said, I'm from Brno University of Technology. We are close here, it's 20 kilometers far away from here, so if somebody wants, it's possible to visit also our university. The faculty is Faculty of Electrical Engineering and Communication and Department of Telecommunications. This is our new building. It's about 3 or 4 years old, so quite new. These two pictures are our laboratory of optical networks or transmission media. Here are places for students. We are teaching 2 courses, transmission media for bachelor students and optical networks for master students. In this part we are mostly doing our research. In 2013 our department has 37 employers, 79 PhD students and 93 new master students and 189 new bachelor students. Our group is called Optolab. We are focusing on optical networks and optical sensors. The leader is Professor Miloslav Filka, then it's me, colleagues Radim Šifta, Tomáš Horvat, Milan Čučka and František Urban. All colleagues except František Urban and except Professor Filka are here, so if you want, you can connect also with my colleagues. What do we are doing? We are focusing on the optical networks and optical sensors, so we are able to do complex testings and analysis of optical networks, design and realization of optical networks, performance testings. We are cooperating with some companies, so we are doing also some performance testing for them and so on. And in the field of optical sensors, we are able to do some measurements of physical events. We are able to design and realize some optical sensors. We also cooperate with the Academy of Science of the Czech Republic in the field of optical sensors. For our simulation or designs, we have some licenses of this simulation software. It's OptSim, OptiSystem, OptiWave, VPI Photonics, and free software like OnNet++ and NS2, NS3, or of course MATLAB. So if somebody needs, we can also design and simulation their network. We are able also to do some traffic analysis or let's say security testings. This is equipment, some basic equipment we have at our department. So avalanche parent is, for example, very good equipment for some security detection and so on. Except some analyzers for RFC 2544 and ultrasound, we can also prepare some other RFC and by traffic generator XCM. Okay, I prepared a presentation where I wanted to talk basically about fiber-optic sensor. I wanted to divide and classify the optical sensor, and the second part I prepared was focused on FBG sensors. Since I think there will be a presentation today or tomorrow or next day after about FBG sensors, I will probably skip this part and will continue to distributed sensors, where I am focusing on FiOTDR system. So fiber optic sensor, probably it's not necessary to mention here all advantages or disadvantages of these sensors. And basically, if we compare these sensors with traditional electrical or mechanical sensors, these fiber-optic sensors has a greater sensitivity. They are totally passive, so there's no difference in other equipments. They are water and corrosion resistant. We can multiplex or these systems together and create one each sensor for different phenomena. This table is borrowed from a book called Fiber-optic Sensors, written by Mr. Wood, and if somebody wants, I have this book here, so if somebody wants, I can borrow this book. And this is a really nice evolution of here's history. When you look, for example, on laser diodes, which is I think the basic component of current sensors. In 1980s, the price of laser was really high. It was about $3,000 each laser. It was mostly a prototype. Now, because lasers were used in printers and compact disc, the price of these components is much lower. And now you can buy laser diodes, I don't know, $1 per laser. It depends on what kind of laser. Single mode fibers also in 1980s, the price of a perimeter was really high, but in 90s there was a telecommunication boom, and because this single mode optical fiber being used in telecommunication, the price of this fiber is now 10 cents. And this is a really nice graph because you can see that the cost of key components is decreasing. On the other hand, the number of possibilities for sensors, for market and low-cost components is increasing during time. So there's a really big perspective for future work in optical sensors. Okay, basically classification. There are many possible classifications of optical sensors. The basic, I think, is on single point. This is, for example, a BG. When you create a BG in the fiber, you can detect even from this location. So this is single point. If you multiply FBGs, you can measure from more BGs locations, and this type of sensor is called quasi-distributed or multi-point sensors. And if the fiber itself is used as sensor, it's called distributed. This is the last case. The second possible classification is on intrinsic or extrinsic. It depends also on the situation. If the fiber itself is used as a sensor, and if the light is directly in the fiber, that case is intrinsic. And for example, this can be, let's say, a repair. There can be some gap, and so light is leaving the optical fiber and then is going to the next fiber. So this is extrinsic fiber optic sensor. Another possibilities is, for example, based on operating principle, we can have intensity sensors, phase, wavelength, or polarization-based optical sensors. We can divide sensors also in the field of application, which, for example, for measurement of physical events or chemical or biomedical, it depends. And also we can divide sensor up to possible measurement, what we want to measure, if it's temperature, pressure, acoustic vibrations, or radiation, depends. There are, of course, we can divide sensor, for example, by cost. If it's low cost, or if it's expensive. This is also worked from book I mentioned before. In this tree you can see the basic dividing of extrinsic fiber optic sensors, and it's divided by principle using for detection. And also under each principle you can find what type of measurements you can do with this kind of sensor. For example, on intrinsic fiber optic sensors, we can divide on the microbed sensors, distributed, that are like more classified on Raman, Rayleigh. There is also Brion, which is missing here, and special kind is interferometric sensors. Since this interferometric optical sensors, it's a really huge area and of optical sensors, I will not mention these sensors in this presentation. I think this topic is on its own presentation. Okay, this is about FBG. I will skip this part and I will go. I can mention, for example, this is a work of our colleagues from Robert Gordon University from UK. They share this information with us because we try to cooperate together, and they prepared a sensor which was based on FBG together with Fiber-optic sensor, and this is used for temperature and pressure measurements. As you can see, the size of this sensor is really very small. And use of fiber gratings, it's almost everywhere, and I think there's a big potential for future work because FBG are mostly used not only in sensor applications but mostly in telecommunications, for example for EDFA, flattening, gain flattening, or compensation of dispersion and so on. Distributed sensors, I think here will be also presentation focused on Rayleigh scattering, so just basic information. When we this kind of sensor uses scatterings, basically there are three types of scattering. Rayleigh, which is elastic one, this means the energy or frequency of the scattering is the same. Another kind of sensors is inelastic. There are Brownian and Raman scatterings, and as I mentioned, these sensors are inelastic. I wanted to show that mostly it's known that there is some FIO-TDR sensor which uses phase changes or detects phase changes along the fiber. But there are also some other possibilities how to use the Rayleigh backscatter. The second possibility is, for example, polarization of TDR, which detects the state of polarizations in the fiber. The problems of this sensor, for example, is that when you detect one event, the state of polarization is changed, and you aren't able to detect next event after this event. But as you can see, by the polarization OTDR, some reported research was measurement which was over 100 kilometers, but it was achieved with using the second order Raman amplifier. Mostly these sensors are for longer distances uses Raman amplifier. OFDR is optical frequency domain reflectometry. It uses tunable lasers, so the frequency of the laser is continuously swept, and we measure reflections from the fiber under test, and then we can use a local oscillator for amplification of this signal. The spatial resolution depends on the tunable frequency of this setup. Raman scattering-based sensing, I think the colleagues from Ostrava, they have one equipment which is based on this kind of scattering. This sensor is called distributed temperature sensing, because you can measure the temperature by this kind of sensor. This phenomena or these scatterings have been discovered by Sir Raman, and he got a Nobel Prize for this. The problem of these Raman and Brillouin scatterings is that they are quite lower compared to the Rayleigh scattering. In case of Raman, it's 20 or 30 dB lower than Rayleigh. Brillouin-based scattering, there are two possibilities how to use this Brillouin scattering. One is Brillouin optical time domain reflectometry, and another is Brillouin optical time domain analysis. The difference between these two methods is that reflectometry uses spontaneous scattering. On the other side, the analysis uses stimulated Brillouin scattering. This is because higher signal-to-noise ratio. But there's one disadvantage, because you need to have access to both sides of the fiber. Okay, I found the last reported really good result using differential pulse with paired Brillouin OTD-A, where the spatial temperature resolution was from 0.02 meters per 2 degrees Celsius over 2 kilometers to half meter per 2.9 degrees Celsius over 100 kilometers. It was again using Raman amplifier. Now I will tell something about Phi-OTDR, or we can call it phase-sensitive OTDR, also phase OTDR, or distributed sensing. There are a number of names for this technique. This technique was introduced by Dr. Taylor and Dr. Lee from Texas University. Later, there were really nice PhD theses from Dr. Juarez, where all these basic informations are really very good described. So for detection, the phase of Rayleigh backscatter is used. The scheme of the setup is very similar to standard telecommunication OTDR. There's one big difference, and it's used laser source, because for the phase sensing you need really stable and ultra narrow spectral with laser source. Of course, since the Brillouin scattering is really low, there are two types of noise. One is electrical noise, which is in photodetector, and the second one is optical noise. This optical noise or optical noises which can be found in a Phi-OTDR. We can divide on phase noise, laser frequency drift, polarization noise, and finite pulse extension ratio. So why it's necessary to use special lasers or very expensive laser with really ultra narrow spectral line width? It's because of power of fluctuations of the phase when the light is traveling inside the fiber, and this is connected with coherence length. So for stable frequency, we need to have a coherent length longer than the pulse width is. Stability. The stability of laser is also very important because let's say we have not very stable laser source. It means you will send the pulse into fiber and you will get reflection. But when the laser drifts in frequency, the second pulse will have little bit different frequency and the response will be quite different. And as I will show you later, if you want to get a really good response from this sensor, you put all reflected traces next to next, and you try to find the phase changes between each 2 or each 10 traces, backscatter traces from the fiber under test. So if you don't have a stable laser, you will get different traces. Polarization noise, it's also very important because if you use, for example, local oscillator for signal amplification, this means you from the laser you will split part of the light and you will mix it with the backscatter light. This can increase the or amplify the signal. But if the state of polarizations is different and are orthogonal, it means that, for example, the sum of these signals can be 0. But there's a possibility using a scrambling, and you can eliminate this effect. And finite extension, this means that you need to create pulses with really high extinction ratio. This is because every time you have one pulse, then 0 or no voltage or no DC component, and again pulse. Every time there is some DC component, and this DC component also is quite negative because it limits your system and distance you are able to achieve. This is possibility for signal amplification, as I mentioned before. It's coherent or heterodyne detection. The principle is very simple because you divide part of the signal with, let's say, frequency, one frequency, and then you, for example, use acoustic modulator, which not only creates the pulses, but it also creates a shift in frequency of the signal. So these pulses have quite a little bit different frequencies. It's about, let's say, 100 megahertz. And since the laser source is is coherent, stable laser source, the backscatter signal is mixed with local oscillator, and the signal can be amplified. This is equation which can be described the mixing of these two signals. So this is intensity of local oscillator and intensity of the backscatter signal, and here we compare the polarization and phase angles of both signals. The important part of each sensor system is also post-processing. There are some possibilities how we can increase the SNR, I mean signal to noise ratio, and for example one is trace averaging. This is possible. It's for example normally used in standard telecommunication OTDR technique, but in our case it's not very suitable because when you average, for example, 10 traces, you will get one final trace, but you are not able to detect, let's say, higher frequencies, because the frequency response of the detected event can be really high, and if you average some, let's say, 10 or 100 traces, your system will be degraded, and they will be able to measure frequencies, let's say, in the order of hundreds of hertz, and something like this. But of course, you can increase signal-to-noise ratio by this. Wavelet denoising method is a possible way for you can decomposing the signal into series of base functions and eliminate noise, and then complete it again without the noise. Now, why is the backscatter signal, why it's problem with its detection? It's let's say we have a very simple scheme as is shown here. So we first amplify the signal to 27 dBm, and then we create pulses. For this we are using acoustic modulator. So we pulses are going to fiber under test, and backscatter is amplified and received by photodetector. Let's say our test scheme has pulse duration about 300 nanoseconds. So when we use equation for this power of power level of backscatter signal, we can count total pulse energy, and from known parameters, because all these are known parameters, we can calculate the received power. And you can see the input power, when input power is 27 dBm and pulse duration is 300 nanoseconds, the received backscatter signal will be about minus 29 dBm, and this is from the beginning of the fiber under test. So the difference against input backscatter signal is very low. Here are next very important equations. It's necessary to mention that speed of the light in the fiber isn't the same as in a vacuum. It's different, and it's depend index of refraction index of the fiber. The spatial resolution is we can calculate by this equation. Basically, for example, if you use pulse with the duration 100 nanoseconds, you can calculate that your spatial resolution will be about 10 meters. On the other hand, if you have 300 nanoseconds, the spatial resolution will be about 30 meters. Yeah, so it's quite easy. And now the repetition rate. Why it's important, this parameter? It's because if you want to receive only one trace from the whole fiber, you need to have a repetition rate. It means you will send one pulse, and then you need to wait this time, and then you can send another pulse. It's because you want to achieve only one trace from the backscatter from this fiber under test. And this is a picture I mentioned before, that if you receive these backscatter signals, you can put them into metric. As in this is let's say 1 million of traces. This is position in the fiber calculated from the known time of the received backscatter signal. And here you can see vibration. This vibration was created by a speaker with a sinus function, and it was about 100 Hertz. So if you want, you can count this. Here is time, so you can count if it's really 100 Hertz, how it is. This is if somebody haven't seen the difference between classic or typical conventional OTDR, so telecommunication reflectometer, for some image analysis. This is response you will get from your OTDR equipment. On the other hand, this is typical response from fiber when we are using phase-sensitive OTDR. I have found also this really nice table. You can find there the research success. As you can see, in 1993, as I mentioned before, Taylor and Lee described using phase-sensitive OTDR for intrusion detection. When you compare sensing range, you can really find that it was achieved 74 kilometers with 20 meters spatial resolution, but also first order Raman was used in this setup. Later, there were recorded also results for 175 kilometers with 25 meters spatial resolution. For this measurement, the coherent detection was used, and for this setup also first and second order Raman and the Brillouin scatterings are used. And now I will introduce you our setup. We had a project. This was financed by Ministry of Industry and Trade, and the start of this project was in 2012 and finished a few months ago. Total budget was 17 million crowns, and it was with cooperation with Czech company ExCom from Brno University of Technology. Mentioned members, basic members of the team. The aim of the project, or annotation of the project, was remotely detect or design detection system for large piping systems for media transport. This system had to be about 100 kilometers reach. Except detection, there were also localization of the event and also classification of the event. So the aim was 100 kilometers, 80% successful detect classification of the signal, and spatial resolution about tens of meters. This means spatial resolution up to 99 meters. So when we started, the first thing was which method we will use. There are possibilities in using Raman, Rayleigh, Brillouin, or some kind of interferometric method. We have chosen Rayleigh scattering for our system. The second step was choosing of components. As you probably know, it's not always easy to choose the right components, because some of these components are really expensive, especially these ultra-narrow lasers. There's a really high price, so if you don't have a chance to taste this laser before, it's let's say, I think about 300,000 Czech crowns, so it's really huge problem if you buy wrong laser. This was really successful for us because we started cooperation with CESNET Association Prague, and they have really good equipment in their laboratory, so they borrowed some acoustic modulators, laser, and so on, and we've been able to test these equipments before buying. So the first problem was the laser diode. What kind of which stability, line life of this laser, and so on. Next was the modulator. will we use some kind of Mach center modulator or acoustic modulator later, because we wanted to use that heterodyne. We needed to use to generate frequency shift of the laser, so we bought acoustic modulator. And also the problem is with EDFAs, because the price is also very high, but is it necessary to use booster and preamplifier, yes or not? Or will be local oscillator enough or not? In our final setup we use also booster, both booster and preamplifier. We had also some problems with passive components because the problems of, for example, optical circulator is the crosstalk between ports. It's better to use quality optical circulators and optical couplers with higher cross extension ratio in crosstalks and others. And since we wanted to put as much higher as it was possible, I mean pulse and pulse power, and it was about 27 dBm. There was also Brillouin peak. So the question was, is it necessary to filter it out or not? And the question was also on optical filters, what bandwidth of these filters should be used, and of course this is really difficult to buy if you don't have your own laser, because you will buy some kind of optical filter and then you will buy laser on different wavelength, and you need to buy new optical filters. In our final setup we also use normal pin photodetector. It was also a question if for these low signals it's better to use avalanche photodiode or pin. In final setup we use pin photodiode with bandwidth about 200 MHz. This is a simplified scheme of our setup. As you can see, this is that local oscillator. First we amplify the continuous wave signal and then we can modulate it. This is due to we bought acoustic modulator with a maximum input power of about 1 optical watt, which is quite enough. Some laboratory tests have been done for about 60 kilometers, and I have to say that this system works perfectly. From the backscatter signal, we needed to amplify this signal, filter out the DC noise, and then we are going to photodetector. There is also some post-processing in the electrical part, and digital acquisition, and post-processing in the software part. This is picture of 100 Hz vibration from a laboratory test. We can see that the total distance was 62 kilometers. The pulse width was 1000 nanoseconds. EDFA booster output power was 27 dBm. We used preamplifier, and we used also coherent detection. The last reported or last results, tested results, has been the measurement was performed on trace between Jihlava, there's mistake, Jihlava, and České Budějovice. The fiber length was in total 118 kilometers, and this system works, let's say, good up to 90 kilometers. The fiber depth was 150 centimeters. It was standard telecommunication fiber, not something special. It was G.652 using for data transmission. The precision rate was 800 Hz and pulse duration 1000 nanoseconds. Here you can see the filtered hammer blow on ground after filtration, and our colleague also prepared frequency analysis, so we are able to do frequency characteristics of the wall fiber. So you can see that the most frequency was 100 Hz, and I'm not sure, but are here some sound speakers? No, probably no. I can try to. It's erased. It's not possible to hear it. Yeah. Can you hear it?
Yes.
It's a hammer. There was a guy after 13 kilometers, and he had hammer and he mowed the ground. And this is a response measured by our system, and then filter this signal. There is setup in our laboratory. You can see also some digital acquisition card and workplace. And here is our acoustic vibration generator of Tesla. And this is the current state of this sensor. It's still quite large, but quite complex. But maybe in future it will be. There is possibility for minimizing, because in this part there's a temperature stabilization, there's laser inside, and also acoustic modulator. There is some place, so maybe, for example, EDFAs which are placed here with some passive components. There's possibility to split it together. This is an ISTA filter which we are using for signal filtering. This can be also replaced by, for example, FPG filter and minimized. In this part there is electrical part where there are some electrical amplifiers, some other electrical equipments, which is not good to present here because this, as I mentioned, this was applied research, so we can share all information. And here is computer for acquisition, with digital acquisition cards and so on. Okay, I will skip this. This is the last paper presented at SPIE Prague. It was focused on signal amplification. It was in cooperation with CESNET, and there were tested three possibilities for signal amplification. It was by pulse signal. The first method was pulse signal amplification by standard telecommunication EDFA. It was because when we in our first setup we used first of all we modulated signal, and then we wanted to amplify this signal. But this standard telecommunication at EDFA had a problem with which caused fluctuations. There were some outages, and the amplification didn't work perfectly. So we used a second laser on different wavelength for EDFA stabilization. Next measurement was pulse signal amplification by the Raman amplifier. So we tried if we are able to increase the distance of our system. The result is yes, it's about 20-30 kilometers with not enough high power of Raman amplifier. And the last one is pulse signal amplification by Raman, by remote amplification. This means we try to use it as is shown here, that the pump laser is placed in, let's say, transmitter part. Then there is 20 kilometers of standard single mode fiber. We tried two types of EDFAs, 10 meter of metro EDFA and 4 meters of highly doped EDFA. And then we tried to use next 40 kilometers. The result is that the optimum pump power was for 10 meters long EDFA was 125 milliwatts auto power, and for 4-meter highly doped erbium fiber was optimal 145 milliwatt. And last slide, this is quite new. Last week our proposal was accepted for financing, so we have new project focusing on security research, and it's the Ministry of Interior of Czech Republic. It will start now in September, and it will take in total 5 years. Total budget is 22 million Czech crowns. It's in cooperation with CESNET Prague, and the goal of this project is to use one optical fiber for data transmission and also for sensing applications. It's due to fiber protection against images. References, and it's all. Thank you for your attention and for your life.
Thank you, Dr. Minister. And now we have a short time for some questions. If you have, please go ahead. I would like. How depend? I mean, was successful your defense of the first project? It should be already made. So
yeah, as I showed before, there is a final equipment, but you know, these systems always need to be let's say being better and better, because the companies, they are working on these sensor systems full time. There are companies who are doing similar systems. They normally achieve about 40 kilometers, 50 kilometers, but there is a team of full members or full employers who can work on this system continuously. In our case, the project is finished, and it's up that company Octocon if they will continue or not. But now the system is operational.
Thank you. Any other questions? If not, thank you one more time.